Hello everyone and welcome to the class of Econometrics 2, Econ 333. This is lecture number 13 and we are going to start with the non-stationarity and unit root. The outline for this lecture is that we will start with the introduction of unit root and non-stationarity. Then we are going to identify the problem of unit root, what unit root is and how we know if a data has a unit root. And we will devise certain tests to find out whether it contains any unit root or not. Then we see how we can resolve for unit root, and that is the process of integration. So in this lecture, we are going to understand what is integration. So let us start with the topic non-stationarity and unit root. Now, there are important differences between the stationary and non-stationary time series. In a stationary time series, shocks will be temporary, and over the time their effect will be eliminated as the series revert to their original long-run mean values. On the other hand, a non-stationary time series will necessarily contain a permanent component. Any change occurring to the series will be permanent, a shift in the curve that will be permanent. Let's say if I want to uh, show that a bit with the help of graph, we have a time series data, we have time factor t, and a certain variable, say x, which is time series variable. So if there is a data and it reverts ultimately to its mean, but if any shocks occurs, it will change its direction permanently. In other cases, if the data is, let's say, um, as a stationary series, and we have a long run moving mean, you can say, and with the passage of time, the data will somehow move around the mean. If any shock occurs, the data can increase but ultimately will come back to its original mean. So the shocks are temporary in a stationary time series, but if it is a non-stationary series, these shocks will be permanent. Then we can say that a non-stationary time series depends on time, which leads to two cases. And the first case is it has no long run mean which the series return to. For example, um, we can say that uh, this is our first case. It does not return to its original mean. And then in the second case, the variable will depend on time and will approach infinity as time goes to infinity. Now, if it has no constant variance and its variance as time proceeds, it may increase over time, or we may not be able to find. For example, this is our long run mean value, but the time series data continues to increase over time. Its variation over long time will be infinite. We may not be able to measure that variation. So these are the say two characteristics that are related to a non-stationary time series. Then we have also discussed in certain ways to identify the non-stationary series. In general, a non-stationary series will follow a theoretical parallelogram that will die out quickly as the lag length increases, while the theoretical parallelogram of a non-stationary time series will not die out. The parallelogram, if you remember those graphs, uh, that we may say dies out quickly for a stationary time series, but for a non-stationary time series, these parallelograms they continue and do not die over the passage of time. So, uh, however, this method is bound to be imprecise because the near unit root process will have the same shape of autocorrelation function as the real unit root process. Thus, what might appear to be a unit root for a certain researcher may appear to be a stationary process for another researcher. So, the point in this discussion is that the formal test for identifying the non stationary, or put it in different word, the presence of unit root, are needed. So in this section we are going to explain what a unit root is and discuss the problem regarding the existence of the unit root in a regression model, and then we are going to develop some formal tests, uh, and we will present them here, and this discussion will be followed on how the results for these above tests can be obtained using e-views. So finally we will test unit root with the help of e-views, and these results will be presented as macroeconomic variables. So we have developed a general idea about the unit root. Let us formally describe what unit root is. So let me write the question. What is unit what is unit root? So basically, let us consider an AR1 model. We can explain that with AR1 model, uh, an equation such as yt equals to theta yt minus 1 plus et. So this is our AR1 model, and in order for this data to be non-stationary, the condition is that the term theta, let me use a different pen to identify that, this term, the absolute value of this term should be less than 1. So that is the condition of stationarity. The absolute value of theta, this should be less than 1. And why is that? I will explain it shortly here. Now in this equation we have the yt, the time series variable, and yt minus 1 is the lag variable. Et is basically the white noise process, and its value will be random. Now let us discuss the three possible cases here. Our first case can be case number 1, that is, what if the value of theta is less than 1? That is our condition for stationarity. And let's say this value is the value of theta is 0.6, and we call it stationary. Why is this stationary? If we want to graph it, we have data, for example, if we want to plot it, and its value will move around mean, and that mean here is 0 because we haven't taken any constant value here, and that value is the constant value is 0. Therefore its mean will be 0, and all the value will somehow uh, move around the mean value 0. If it does have any constant term, for example, if we include alpha over here and alpha's value is um 10, then it somehow will move around the mean value of 10. Anyhow, the concept here is that the data will be stationary, it will move around a certain mean. Then we can have a second case, and that is when we have case number 2, the value of theta that is greater than 1, and if it is greater than 1, each consequent each consequent value of yt will be greater than yt minus 1. For example, if we have theta is equal to 1.5, then if y t minus 1 is equal to if yt minus 1 is equal to 1, then yt will equal to 1.5, and then yt plus 1 will equal to 1.5 multiplied by 1.5. So it will continuously increase. It will grow by 50% each time. And what we if we want to graph it, what we will get an exploding series, that the value will always be increasing and increasing at a it will show a growth rate. So the series will explode. The value of y will continue to rise until infinity. So that is our second case. Then we can have a third case where the value of theta that is exactly equal to 1. In this series, again, it contains a unit root and is non-stationary. And why is this non-stationary? Because again, if you want to graph it, it has a certain value, but then it has a random term. The data will somewhat look like increasing with random variations. Because it is equal to 1, the value will actually equal to its last value, but will continuously increase with certain variations. So again, this data is not stationary. Now, in order to make this data stationary, what we can do, we can take difference of the time series variable. So let me show what happens when we take a difference of a time series variable. We have equation yt, and yt, as I have shown above, equals theta yt minus 1 plus the random variation term, the white noise process. Now, if theta equals 1, let's say it has a unit root and theta equals 1, we get a graph like this one, as I've already discussed it. Let us make it a stationary data, and what we will get, yt is equal to 1 yt minus 1 plus et, and taking difference yt minus yt minus 1 is equal to again yt minus 1 plus et, taking the difference over here as well. So this is yt minus 1, these two cancels out, and so what we get here is the difference of yt, and that equals to et. Now you can see that changes in yt is purely random, and we know that et is a white noise process, and a white noise process has a mean equal to 0, and its variation is random. So you can say that it has a mean of 0, and the values of yt series will move around this mean. So we have made the data stationary. Now we cannot always make the data stationary with the first difference. Sometimes it takes uh, a second difference to make the data stationary. Sometimes we require to difference the data for third time in order to make it stationary. So here is a definition uh, that we may say that a series yt is integrated of order 1 uh, and contains a unit root y if the value is non-stationary but the first difference is stationary. So let me write that for you. We have series yt and we say that it is order integrated of order 1 if it becomes stationary on the first difference. If it becomes stationary on the second difference, we may say that it is integrated of order 2. So integration basically means how many differences are we going to take for a data to become stationary.